All right, this is example problem 2 from lecture 23. So we're asked to find the moment of inertia about the horizontal centroidal axis for an I-beam that's made of 3 2-inch by 8-inch pieces of steel plate, right? So the way we're going to do this is we're going to break it up into a plate A, a plate B, and a plate C. We'll find the moment of inertia for each of A, B, and C individually, and then we'll add them all together to get the moment of inertia for the composite shape. So we're going to start with plate A, and we're going to say that the moment of inertia about the centroidal x-axis is going to be the base times the height cubed over 12. So just like in example 1, the term that's getting cubed is the one that references distances going away from the axis of rotation. So for this, that's the 8 inches, because that 8 inches is the one that shows how much area is getting moved away from the axis of rotation. So we have 2 inches times 8 inches to the third power all over 12, which gives us 85.3 inches to the fourth. All right, and then so for shape A, it's already positioned at the centroidal axis, so we don't need to do anything else. For shape B, we have the moment of inertia about the centroidal x-axis is the base times the height cubed over 12. So for this one, it's rotated 90 degrees from what A was, right? So we know we have to flip which ones are base and which ones are height in our equation. So for this one, we have 8 inches times 2 inches to the third power all over 12, which gives us 5.33 inches to the fourth. So at first, it looks like shape B isn't giving us nearly as much contribution to the moment of inertia as shape A is. However, this is calculating the moment of inertia about the centroidal x-axis, which for shape B is all the way up here. If we want to calculate about the actual x-axis for the whole shape, we need to use the parallel axis theorem, where the moment of inertia is equal to the centroidal moment of inertia plus the area times the distance that the rotational axis shifts squared. So for this one, we have 5.33 inches to the fourth. The area for a rectangle is its base times its height. So 2 inches times 8 inches. And then the distance that it's shifted is this 5 inches given on the diagram. So 5 inches squared. And if we go through all that math, we get that the moment of inertia for shape B is equal to 405.3 inches to the fourth. So just like that, now we see how B is contributing far more to the moment of inertia of the composite object than it would have been if it had been at the centroid axis. So again, this is why we have these flanges on steel beams. We're adding area far away from the axis of rotation. If we go ahead and look at shape C, we see that it's symmetrical. C is the exact same shape as B is, just above the line instead of below it. So the moment of inertia for shape C is equal to the moment of inertia for shape B. So again, if we want the moment of inertia for the whole object, we're going to take the moment of inertia contribution from A plus the moment of inertia contribution from B plus the moment of inertia contribution from C, which will give us 85.3 inches to the fourth plus 405.3 inches to the fourth plus another 405.3 inches to the fourth. Add them all together and we get 896 inches to the fourth. Right? So by adding those shapes B and C, we've gone from a moment of inertia that's just 85.3 and increased it by a factor of 10.